Hey everyone, welcome back. Today we're going to dive into something pretty incredible. An AI system that's not just about treating problems after they happen, but about seeing a life-threatening medical error coming and stopping it cold.
So, picture this. You're in the hospital, maybe for something pretty routine. They give you a common medication, everything seems to be going just fine. But what you don't know, what no one might know, is that under the surface, a serious danger is brewing, one that could turn a simple recovery into a full-blown emergency. To really get our heads around how this all works, let's talk about a real-world example. Let's meet Sarah. She's 68 years old, and she is right at the heart of our story today. Her life, and this is no exaggeration, hinges on a system's ability to connect the dots in a way that even a busy, brilliant doctor might miss.
Okay, so here's the deal with Sarah. On the surface, everything about her case seems completely standard. She has an irregular heartbeat, atrial fibrillation, so on day one she gets a prescription for warfarin, a very common blood thinner. A couple of days later, she mentions some chest pain, so another doctor adds aspirin. Both are totally normal procedures. But here's the catch. Together, they create this hidden, ticking time bomb, a major risk of a life-threatening bleed.
So you've got to be asking, how on earth does an AI even start to see a risk like this? Well, it all begins with the first crucial step, getting to know Sarah. And that means taking all the messy, scattered, chaotic pieces of her medical file and turning them into something that actually makes sense.
This whole process of making sense of the data unfolds in three key stages. First up, you have the bronze layer. Think of this as the giant digital inbox where everything gets dumped. Her electronic health records, lab results, the doctor's scribbled notes, you name it. Then it moves to the silver layer, where all that messy data gets cleaned up and, really importantly, standardized, so every piece of information is now speaking the same language. And finally, you get the gold layer, where it's all organized into these perfect, analysis-ready tables that the AI can use in a split second.
You know, to really paint a picture here, the change is like going from a super messy garage to a perfectly organized library. In that garage, the bronze layer, everything's probably in there somewhere, but good luck trying to find anything when you actually need it. But the library, the gold layer, well, now everything is cataloged, easy to find, and totally ready for some serious analysis. This foundation is absolutely crucial for everything that's going to happen next.
Okay, so now we have this beautifully clean, organized data. Awesome. But, just having a list of facts isn't enough, right? The system has to understand the relationships between all those facts. So this next phase is all about building a kind of relationship map of Sarah's entire health journey.
And the special tool for this job? It's called a knowledge graph. Now, don't let the fancy name fool you. The idea is actually pretty intuitive. Think of it less like a spreadsheet and more like a social network for medical info. It doesn't just store isolated facts. It actually maps out how every single thing, every patient, every drug, every diagnosis is connected to everything else.
So let's build this out, piece by piece. It all starts with a single point, a node in our graph, Sarah herself. Next, we add a relationship. The graph now understands that Sarah takes the medication warfarin. Simple enough?
Now this is where it gets really, really smart. See, the knowledge graph isn't starting from zero. It comes preloaded with vast amounts of medical knowledge. So it already knows that the drug warfarin has a dangerous interaction with another common drug, aspirin.
So literally the second that new aspirin prescription hits the system, it's like a chain reaction. The graph sees Sarah, who takes warfarin, and it knows warfarin interacts with aspirin, and boom, the system instantly sees the dangerous connection and triggers a critical alert. A regular old database could never, ever do that.
But look, just getting another alert isn't always enough in a busy hospital. To be truly useful, the system has to go one step further. It needs to calculate the actual level of risk. And this is where we move from just connecting the dots to actually predicting the future using machine learning.
And this is what it comes back with. The AI looks at all those connections in Sarah's graph, her age, her recent lab results, and of course, these two medications, and it calculates a staggering 87% predicted risk of a major bleeding event. Wow, a number that high is just impossible to ignore.
Of course, if you're a doctor, the very next thing out of your mouth is going to be, okay, but why? Why exactly 87%? And that's a perfectly fair question. No clinician is going to trust a prediction that comes from a black box. To build that trust, the AI has to show its work.
And it does. It uses a really cool technique that basically breaks down how it made its decision, giving everyone a clear explanation. It shows that the warfarin prescription is the biggest driver, adding 28% to her risk. The new aspirin tacks on another 22%, and even her age contributes 15%. All of a sudden, that big 87% number makes total sense. So now that the doctor gets the why behind the number, the system's job is to help them figure out what to do next. It's about turning that prediction into a clear, actionable plan.
So the doctor, looking at that breakdown, is naturally thinking, okay, that aspirin is clearly a big part of the problem. What happens if I just stop it? The system is designed to answer exactly these kinds of what-if questions.
And boom, here's the answer. The system runs a quick simulation and shows that if the aspirin is discontinued, Sarah's risk plummets from that critical 87% all the way down to a much more manageable 35%. It gives the doctor a clear, data-backed path to make their patient safer right now.
What's just mind-blowing is how fast all of this happens. Take a look at this timeline. At 2 p.m., the aspirin is prescribed. Just 1 minute later, the system has already calculated that 87% risk. Within 3 minutes, a full explanation is generated and an alert is on its way to the nurse's station. And by 2:15 p.m., just 15 minutes from the initial mistake, the doctor has seen the data, understood the risk, and canceled the medication. A crisis completely avoided in minutes.
So the system saved Sarah, which is incredible. But the story doesn't end there. For an AI to get truly great, it has to learn from thousands of patients just like Sarah across tons of different hospitals. And it has to do all of that while protecting patient privacy like it's the most important thing in the world, because it is.
The solution here is a really clever technique called federated learning. Here's the basic idea. Each hospital trains the AI model on its own private data. But instead of sharing that super sensitive patient data with anyone, they only share the mathematical improvements, the learnings, from the model. This lets the main AI model get smarter and smarter from the experiences at every hospital, without a single piece of Sarah's personal information ever leaving her hospital's secure servers. It's brilliant.
So the real takeaway here is that this isn't about one single magic algorithm. Not at all. It's a complete system working together. You start with that solid data foundation to organize the mess, use a knowledge graph to find those hidden relationships, you apply machine learning to predict the future risk, you have explainability to build trust with the doctors, and automated systems to deliver alerts in real time. And you wrap it all in privacy tech that allows everyone to collaborate without compromise. Every single piece is essential.
Which leaves us with this one last really fascinating thought. Sarah's case was about 2 of the most common drugs on the planet. So it really makes you wonder, what other dangerous combinations, what other hidden medical risks are out there right now, just hiding in plain sight, waiting for the right kind of system to finally connect the dots?